Okay, so we're going to be dealing with a section on work. I think it's 7.5. Okay, the very basic, or the simplest definition, but also the least useful, is algebraically work equals force times the distance over which you apply it. This particular one is useful if you have a constant force acting in the same direction as the movement, which is a rather limiting characteristic. But we can do an example of one like this. So if I've got a constant force, I'm applying a constant force of 30 newtons. By the way, grams is not a force, it's a mass. To convert it, you have to multiply your mass times 9.8 meters per second squared. But 30 newtons over 5 meters. And to do this, it's a constant force that's acting in the same direction. So my work is going to be 30 times 5, which is 150 Newton meters. Okay, pre-cal, we change this up a little bit in that I could have a force of 50 newtons, but it's acting, moving this way, but it's being pulled at an angle 30 degrees up. And let's go ahead and keep this as 30. And we're going to work over 5 feet. So here work is defined to be the dot product of these vectors, or work is going to be equal to FD times the cosine of the angle between them, which in this case is going to be 50 times 30 times the cosine, 50 times 5, times the cosine of 30 degrees, which is going to be 150 times the square root of 3 over 2, which is going to give us 75 times the square root of 3 Newton meters. Okay, now this again is still assuming a constant force. In other words, the force never changes. This is not usually a very good assumption. And let's work a nice example. We got a building here. Calculus instructor's at the top. And he's got a student at the bottom. He's tied a rope around his neck. He's going to pull him up. And this total distance is going to be 10 feet. The student weighs 200 pounds. But loses weight on the way up. And I'm not going to specify how he loses it. At the rate of 2 pounds per foot. In addition, 5 pounds per foot. Okay, so weight is a force. It already has gravity in on it, which is why you weigh less on the moon than you do on the earth. It's a force. All right, now you can tell we're not going to have a constant force because, well, it starts out at 200 pounds. Somehow or other, we're getting rid of some of this weight at 2 pounds per foot. Now, we also have the rope. Okay, it weighs 55 pounds per foot, but as we pull it up, I'm going to have less and less and less weight. So what you need to do with this then is to break this down into your individual components of your weight. So my weight is going to equal to the weight of the student at some particular height plus the weight of the rope. Now you may think this is kind of trivial, but this little step could save your butt if you're not careful. Okay, so let's find the weight of the student. So at the bottom, and now we start at the 2 endpoints. The weight is 200 pounds. At the top, not at pop, at the top, the weight is going to be equal to 200 minus the rate at which he's getting rid of it, which was 2 pounds per foot, times the height, which was 10. So he's now going to weigh 180 pounds. Okay. So now let's take a look at the rope. As you can see, we're losing weight. Okay, at the bottom, it's going to be 5 pounds per foot times, I've got 10 feet of it hanging down below me, which means it's going to weigh 50 pounds. At the top, it's going to be my original weight, which was 50 pounds, minus the 5 pounds per foot I lost, times 10 feet, which means it's going to have no weight at all at the top. Okay, so what I do then is I come in and I especially take a look at these guys right here for getting my equations, because they basically already give it to you. Okay, so the weight of the students at some height x above the ground is going to be, this is the weight of the student, 200 minus the rate at which we're losing it, which is 2, times the height, which is x. And the weight of the rope at some height x is going to be what we started with, 50, minus 5 pounds per foot, the rate at which we're losing it, times our height x. So now our total force, which is our weight, is going to equal to weight of the student plus the weight of the rope, which is going to be 200 minus 2x plus 50 minus 5x. And then I come back in, and this is force as a function of x. And I end up with 250 minus 7x. And there's my force. And this is where most of your time and energy will be spent, is on the force. Okay, so this is an important little distinction. What I'm going to do here is pick some arbitrary point. So arbitrary height, x. And I'm going to move him up a very small distance, dx. So the work done in other words, my instantaneous work at some point x is going to be equal to my force times my distance, which is dx. So my instantaneous weight is going to equal to 250 minus 7x dx. There's my force times my height, or my distance. Because I'm only moving him a very small distance. So to get the total work, we're going to have to integrate this. And we looked at our bounds. We start at 0, and I'm going to go up to 10. So it's going to be integral from 0 to 10 of 250 minus 7x dx. What you find for most of these, once you get in and actually start working with them, the actual calculus is going to be pretty easy. Here's my thing. I need to do my integrals. So I'm going to end up with 250x evaluated from 0 to 10 minus 7 halves x squared evaluated from 0 to 10. Which is going to give me 250 times 10 minus 0 minus 7 halves 100 minus 0. It'll give me 2,500 minus 350, or my work is going to be, I calculated it, 2,150 foot-pounds. Okay, so now let's take the same basic problem, but let's change it a little bit. Instead of losing weight, the other calculus students are shooting at him, okay? And they're actually pretty good shots, because now the student gains weight at the rate of 10 pounds per foot. Okay, so it's the same basic idea that we had before. All right, so the weight of the student at the bottom is still going to be 200 pounds because you haven't done anything. The weight of the student at the top is going to equal to the 200 pounds plus 10 pounds per foot times the 10 feet. So he's going to weigh 300 pounds by the time he gets up to the top. The rope is the same thing. We're not doing anything to the rope. It's going to weigh 50 at the bottom, and it will weigh 50 minus 5 times 10, which is 0. So my force now is going to be the weight of the student, which is going to be 200 plus 10 times the height plus 50 minus 5 times the height. And again, I come back in. It's going to be 250 plus 5x is my force. And my instantaneous weight then is going to be this force, which is 250 plus 5x times dx. What my total work is going to be the integral from 0 to 10 of 250 plus 5x dx. Now we do our integration. So I'm going to have 250x evaluated from 0 to 10. You notice this is the total combined weight of the student and the boat. Plus 5 halves x squared evaluated from 0 to 10, which is going to give me 250 times 10 minus 0 plus 5 halves times 100 minus 0. It's going to give me 2,500 plus 250, or we're going to do 2,750 foot-pounds of work. All right. This is, believe it or not, actually a relatively intricate question. If you can just break these into the different pieces, they'll be easy. I'm going to work one more example then. This is an excellent AP question. As in, they really like to put questions like this on the test. So we are dealing with an exercise machine here that has a spring in it. All right. And what we know is that a force of 20 pounds, which they can actually measure, stretches the spring 9 inches. You want to find the work done in stretching the spring one foot. Now you notice this is in inches, so we should convert this to 12 inches. All right. So there we've got this thing. Now, I'm not sure what you were taught in physics, but springs, you do not have a constant force. It takes more force as you get farther and farther away. And your force for a spring is governed by Hooke's law. And all Hooke's law said is that the force is directly proportional to some constant, this is your spring constant, times the distance that you've either stretched or compressed it. So there's our force. All right? Now, we don't know K, but we can find K because we were given this. So 20 pounds is equal to K times 9, or K is 20 nines. So our force, the sum function of x, is equal to 20 over 9 x. All right, so with that said then, let's come back and find our work. Believe it or not, this is the hardest part. Finding the work then is just going to be the integral over the distance and removing it 1 foot, which is 12 inches. So 0 to 12, make sure you have consistent units of my force, which is 20 over 9 x and the differential distance dx that we've moved this thing. Okay, or my work is 20 over 9 times the integral from 0 to 12 of x dx. Well, this one doesn't look too bad then. So w is going to be 20 over 9 times 1/2 x squared evaluated from 0 to 12. Or my work is 10/9 of 144 minus 0. And that worked out to be about 160 inch-pounds. Okay, most of your effort in finding work is going to be in finding the forces. These variable forces. So, your force laws that you're going to be dealing with, Hooke's law for the spring. If you want to put something into space, you use Newton's law of gravitation. These are in your book. If you're dealing with work done by compressing or expanding gases, you'll deal with Charles' law. And for some electrical work, you'll be dealing with Coulomb's law. And these are all in your book. These are all inputs. These all give your force as a function of distance. And then to do these now, once you find the force, all you got to do is integrate that puppy over your two bounds of your f of x dx. All right? And these integrals usually are pretty easy. This is one case where much of your work will be done at the beginning, will not involve very much calculus, and then you're basically going to have one calculus step near the end, and then you're done. So this should get you through the first assignment. And remember, take your time. Take time to get your force equation. All right? Once you get the force equation, the actual work part of it is really easy. And they're usually nice, simple integrals.